Welcome back. This is going to be the last video on our chapter on exponential smoothing. Let me kind of begin with a summary of what we've done in this chapter. So the first module was on simple exponential smoothing, and we use that when there's really only a cyclical component present, when there's not a trend component present or seasonal components present. Then we moved on and we covered something called the Holt method for when there is a trend as well as a cyclical component. In the previous video, we talked about the Holt-Winters method, which extends the basic Holt method by also allowing for seasonal effects. All three of these approaches are really just algorithms. There were no, I never stated a statistical model at all. I gave an algorithm that just said, for example, with simple exponential smoothing, my level at time t is just going to be the current information that just came in at time t times some alpha plus 1 minus alpha times whatever I knew before. And so that's just a simple algorithm. This last section develops statistical models that subsume these three models that we've already covered. So these models are called ETS models. ETS means air, trend, and seasonal state space models. So unlike the methods that I've talked about, which are commonly referred to as exponential smoothing methods, these are statistical models that assume a very specific probabilistic distribution that gave rise to the data. I'm not going to get into the details of exactly what that distribution is and how it came about. The author in this of your textbook sketches out some of those details and also has a more advanced book where they develop the theory for this. Now, these kind of more general models, these ETS models that subsume everything, have a number of advantages. So the first is that they allow us to make prediction intervals. So the previous methods that I had, they were just algorithms, and we were getting prediction intervals when I was making the plots in R, but I didn't show you how to get those from the algorithm. That really has to come from these state space models. The second big advantage that we're going to have is a more general process for automated model selection. So these are, very powerful models that we're covering here. To give us some sense of what's going on, we can think about three possible components to our models. So there's an error component, and the errors can either be additive or multiplicative, as we've seen throughout the course. So are we multiplying by the errors, or are we adding the errors to whatever model we have? So it could be a trend plus season, but then how do we add an error component to it? Second part is a trend. Now, really we've had three different trend possibilities. So the first is there is no trend. For example, when we did simple exponential smoothing, we did not account for a trend. The second trend is to have an additive one, and that's exactly what we did with the Holt method. During that unit, we also covered damped trends. So the damped trends start out extrapolating basically linearly, but then they flatten out over time and approach an asymptote. So that was the damped trend method. When it comes to seasonal effects, we also had three possibilities. So no seasonal effect, and that's what we did with SES or Holt methods. But we also had the Holt-Winters method, which allowed two possibilities. So the seasonal effect could either be additive, where we change, for example, every December goes up by a fixed amount, or multiplicative, where we multiply by some index that, for example, December might be 20% greater. Now, if we think about these three models, which we're going to be identifying by a triple. So what is the air component? What is the trend component? What is the seasonal component? Across all these possibilities, we end up with these 18 models. It would be 3 times 3 times 2. So you can have the air component being additive or multiplicative times 3 trend components times 3 seasonal components. And that would give 18 total possibilities. Let's just look in a little more detail about these possibilities. The first one I bold-faced, which is ANN. So what that means is we want an additive air. We don't want any trend, and we don't want any seasonal component. Well, that's just what we called SES before. The Holt method is going to be sitting right here, where we have an additive air and an additive trend without any seasonal part. The third line gives us the damped trend method that we talked about. So again, no seasonal part, additive air, damped trends. We've met 2 other models so far in this class. So the Holt-Winters model with an additive seasonal effect is going to be the AAA model. The Holt-Winters multiplicative model that we covered earlier is going to be the multiplicative additive multiplicative model. I'll just mention these models in the upper right where we have a multiplicative trend component don't get used. So instead of 18, we really have 15 models. There are a lot of other models out here that ETS will allow us to consider. So for example, we could have an additive air without a trend, but a seasonal component. Likewise, we could have a number of other combinations. How do we estimate these models? Well, there's a very nice function in the forecast library called ETS. ETS has the following parameters in red. And so you can set these values to null if you don't want to consider them. Or you could specify them if you want to specify, for example, an alpha. So alpha, beta, gamma are the smoothing parameters. Phi is going to be our dampening parameter. Initial states are going to get estimated. As with all of our other forecasting functions, we can ask it to find the Box-Cox parameter with the lambda. So if we say lambda equals auto, it will go find it for us, or we can specify, for example, 0 for a log model. See the textbook for much more detail about exactly what the likelihood function is and how we get the prediction intervals. Another argument that we're going to want to use is the model argument from time to time. So if, for example, you really wanted the SES model, you would say model is just ANN. If we don't specify a model argument, it will do model selection for us. And the way it's going to do it is try all the models and choose the one with the best AIC, corrected AIC value. Well, let's jump into a couple examples. Back, I guess this was with the Holt method, we looked at the shampoo data set. I thought this data set was kind of interesting because what we see is the plot is basically fairly flat, but then the trend starts to increase over time. And so we needed a trend that was flexible in order to capture this. Well, let's go try fitting an ETS model to this data, and we'll let it choose its own lambda. When you display the fitted object, you'll see that what we get is the best model has an additive air, an additive trend, and we don't need any seasonal component. We'll see that the ETS function chose a Box-Cox transformation of about 0.27, so somewhere between a log and a square root. So we need to stabilize the variance a bit, and we can see what our smoothing parameters are. The smoothing parameters are both set to be 0.0525. And what that's saying is the level and the trend don't need to be that sensitive to the current values. So we're giving 95% of our weight to the previous values and only 5% of the weight to the latest value of either the level or the trend. Another thing that I think is kind of interesting is that we actually get the values of the level and the slope, or the trend, whatever you want to call it, at different time points. And so this is all stored in the states command. But these get plotted when you do an auto plot of the object. And so let's go take a look at what we get here. The level you're going to see is kind of flat and then starts increasing pretty rapidly. We can also see the slope. Now, one thing to note about the slope is it sure looks very jagged, but notice how small the scale is. So this is minus 0.1 to positive 0.3. So the range of this graph is only about 0.4, whereas the range of the level plot is, what is that, about 5 or 6? And the observed values are clearly even more variable. So what we see with our slope, whether we look at this plot, I really like the plot, or if you want to go look at the raw data, is that the slopes are actually starting out negative. And so it looks like there's an initial decrease in sales, very slight decrease in sales. You see they're not really negative, but just slightly negative. But then after a couple periods, there's a clear increasing trend. And so you're going to see the slope goes positive and goes up for a while, and then I see the slope flattening out. The way I see this is over here, it's getting steeper, and then it just flattens out at a slope of around 0.3 or so. That's the shampoo data. Let's go take a look at the retail data set that we looked at in the previous video around Holt Winters. So I'm going to start out by simply estimating ETS. We'll let it do whatever ETS wants. And it comes back with a model that we've never seen before. So this model has multiplicative errors. It says we really don't need a trend. So there's no real trend happening as long as you take care of the level part. And we're going to use an additive effect for the seasonal effect. So it's kind of interesting. MNA, you're going to see, was not one of those models that we'd had before. So MNA would be down here somewhere. MNA. Anyway, it's somewhere in here. MNA, right here. So if we go look at our smoothing parameters on this data set, you're going to see a fairly strong alpha. We're going to pay a lot of attention to the most recent level. Not much of a change in the seasonal effect. So the value of gamma, which is the smoothing parameter for the seasonal part, is very, very small, indicating we're going to give basically the same amount of weight across the board, across all time periods. The most recent value gets almost no weight. If we go do an auto plot, what I think is really clear is the financial crisis. And so the level is showing a bit of an increasing trend until about 2008. Then the bottom drops out, and then we see a trend increasing again. We can see our seasonal effects, and the seasonal effects don't change much. Again, that's reflected by the very small gamma values that we have. Another possibility would be to impose a log transform on it. So I'm going to refit this model, this time specifying lambda equal to 0, meaning take the log first. What we get now is another model that we haven't seen before, additive, no trend, additive seasonal. And so remember, once you log a multiplicative model, you get an additive model. And sure enough, that's what we get. Seasonal effect is pretty similar. Alpha is maybe slightly smaller, but still, you're giving the majority of the weight to the most recent case. Other thing what we could look at is the training set error values, and it appears the multiplicative model is marginally better than the logged additive model. So I would, I guess, trust the ETS function on this one and go with the multiplicative model without a trend, but additive seasonal parts. Let's go take a look at another example that we've looked at many times in the past, which is the Amazon sales data. I'm going to let ETS choose a Box-Cox transformation. We know from previous analyses that that's a fairly important part because we have some exponential growth with Amazon. So after taking a Box-Cox transformation, what Box-Cox wants is AAA. And so that's basically what we found before, that logged or Box-Cox version of AAA for the Holt-Winters additive model works pretty well. What this is saying is we don't need to do much more to it. We have a level that's increasing very steadily. The slope is fairly constant from 0.08 to 0.11-ish. Maybe the slope is slightly increasing after taking the Box-Cox transformation, but not by much. It's showing a steady positive slope, and that's exactly what we see in this level plot. One thing that is interesting about this is the estimated gamma parameters. So you're going to see gamma is fairly large, 0.35, meaning give roughly a third of the weight to the most recent seasonal values. Give the remaining 2/3 to what you had before. And so what we see in the seasonal plot is the amplitude of this is changing. It looks like the amplitude gets a bit greater around 2010, and then you see reduced seasonal effect beyond that. Maybe they've diversified their portfolio so it's not as dependent on just Christmas. But that's kind of an interesting effect, and it shows up very clearly in this plot. One last example that I want to go over with you is a drug sales data set from our textbook. So this is in the libraries that come with the textbook. It's called HO2. So here we are, and let's start by just looking at what's in the data set. What we see is clearly a lot of seasonality. I also see maybe a bit of heteroscedasticity. Perhaps, I'm not completely sure about that, but there's a very strong seasonal component to this. Let's just go fit an ETS model, and let's see what we got. So the ETS model comes back with a multiplicative error, a damped trend with multiplicative seasonal effects. So that multiplicative seasonal effect is going to capture the heteroscedasticity that I was seeing. So as the mean increases, the seasonal effects are going to get bigger. What we see from our smoothing parameters is that the slope and the trend part, the seasonal part and the trend part don't change much over time. The level does a bit. So we're going to give a fair amount of weight to the most recent observation. And it looks like it helps to use the damped trend. We don't want to just do a straight trend. Well, let's go take a look at the plot of this. I'm going to fit a second model as well. We'll take a look at that as well. If you want to specify a specific model, you can say model equals, for example, AAA, which would give us the Holt model with additive seasonal effects. Well, let's go take a look at the plot. And so what we see is the level is increasing but the slope flattens out. So when we go look at our slope, the slope begins fairly steep. That's what we're seeing right here. The fact that the slope is diminishing is saying this the level of this function, it goes up for a while and then it flattens out. So when you have a slope of 0, that means you have a flat trend, and so we're seeing that. Beware. So most of the variability is in the level part and the seasonal part. There's very little variability in the slope. And you can see that also in the axis over here. So from 0.000 to 0.008, whereas the seasonal effect varies substantially more, as does the level. Levels varying by about 0.6, as is the seasonal part. We can create forecasts and see where this is going, and so we get those with prediction intervals shown in blue. Let's compare the accuracy of this model with the basic Holt model with the seasonal part, so the additive seasonal part. And so what we see is that, at least on the training data, this this model that has a multiplicative effect with a damped trend is beating the basic Holt additive model by a little bit. So 0.05 versus 0.06 if we trust the training set error. So in the training set, we're doing a little bit better. Another thing we might want to do is have a test set. So as we saw with the Amazon data, it's really important to have a holdout period. So I'm going to use the data through 2004 as my training set and the rest of it as my test set. So we'll go estimate the ETS model using only the training set. Let's compare it with the Holt model with an additive seasonal part. And then I'm going to now compare the accuracies only on the test set. So if I do that, what we see is what the training set was telling me is true of the test set as well. So RMSE goes from about 0.091 up to about 0.14, so about a 50% increase in RMSE. MAE likewise shows an increase on the test set. These ETS models that allow for possibilities that Holt-Winters does not allow for is very important. Let's go take a look at the forecasts of how we're doing on this. And so what we see is we are capturing the seasonal part and the trend. So I think we're doing a decent job on this. I could have added the original data. In fact, why don't I do that? I'm going to go HO2 here. And so here we get to see how our predicted values match up with the observed values, and it's looking decent. So instead of doing 10 periods, let's do, say, 40 periods. And so what we see is that our predicted values are doing a pretty good job on this. All right, that's it for my video on ETS models.